For 2 full decades, a dramatic and persistent story has circulated in aviation circles that one of the first Airbus A320s delivered to China mysteriously vanished from public view. Never seen flying again, never registered on a commercial route, simply gone. Aviation insiders began calling it the ghost plane. The theory that the aircraft was quietly taken apart, studied piece by piece, and used as the blueprint for China's first homegrown commercial jet, the COMAC C919. It sounds like an international thriller complete with industrial espionage and high-stakes geopolitics. But is that really what happened? And if so, why has the C919, after all that, still failed to take off on the world stage? To understand the stakes, we must first recognize how vital single-aisle aircrafts are to global travel. These aircrafts, called narrow-body jets, carry passengers on short to medium-haul routes that make up the bulk of daily airline operations. They serve flights under roughly 6 hours, the kind of route thousands of travelers take every day between cities like New York and Miami, London and Rome, Beijing and Shanghai. The 2 dominant families are the Airbus A320 and the Boeing 737 family. These aircrafts define the backbone of most fleets worldwide because they are efficient, reliable and backed by decades of operational experience. Airlines invest tens of billions of dollars in these platforms, and the global infrastructure, from pilot training to spare parts to maintenance, revolves around them. When a new manufacturer tries to enter this segment, they are not just introducing a new plane, they are challenging an ecosystem decades in the making. China's aviation manufacturing arm, Commercial Aircraft Corporation of China, COMAC, developed the C919 as the nation's first large modern passenger jet intended for mainstream airline service. It represents a substantial industrial and technological achievement for China, but the extent to which it challenges the Western duopoly must be examined realistically. The aircraft first flew in 2017 after years of development, marking a milestone for China's aviation ambitions. Development of a modern airliner from concept to flight test requires coordination of design, aerodynamics, systems engineering, manufacturing, certification, and supplier integration, a process that often takes more than a decade even for well-established aerospace companies. One persistent narrative suggests the C919 is essentially a reverse-engineered copy of the Airbus A320. In industry terms, reverse engineering means taking an existing product apart to understand how it works, and then using that knowledge to create a functionally similar product. In aerospace, this is not a simple or straightforward shortcut. Aircraft's designs are protected by extensive intellectual property, patents, and regulatory oversight. Manufacturers share technical data with customers and suppliers under strict legal agreements. The idea that a single aircraft disappearing from radar would provide enough insight to duplicate an entire airframe, and its complex systems is technically and legally unlikely. Aircrafts are more than their visible components. They are systems of aerodynamics, certified materials, software, and regulated safety margins that cannot be deduced simply by inspecting parts. What is more accurate is that China's aviation industry studied Western aircrafts extensively as part of its education and industrial strategy. Engineers learn from existing technology worldwide. This practice is common in aerospace. Design evolution often builds on lessons from predecessors and competitors. However, the leap from studying or even disassembling parts to producing a fully certified, reliable commercial aircraft is huge. A critical detail often overlooked in sensational stories is the role of foreign suppliers. Modern aircrafts are global products. Even Airbus and Boeing source major systems from international partners. Engines, avionics, landing gear, flight control computers, and many other subsystems come from specialized manufacturers. The C919, like many aircraft programs, uses components from international suppliers. For example, its engines are derived from Western designs produced under commercial agreements. Avionics and certain flight control systems also come from established foreign manufacturers under license or partnership. That means the aircraft is not a purely domestic creation. And it also means that technology transfer is governed by contracts and export regulations. Because these suppliers carefully control what technology they provide, the C919 does not incorporate the absolute cutting-edge systems found on the very latest A320neo or 737 MAX variants. Instead, it uses proven, well-understood components that are suitable for commercial aviation, but do not provide a performance advantage over its competitors. Even if two aircrafts look similar on paper, certification is where the real difference becomes clear. Aviation authorities like the European Union Aviation Safety Agency and the US Federal Aviation Administration have extremely stringent standards for safety, performance, testing, and documentation. To operate in many international markets, an aircraft must meet these regulators' certification requirements. COMAC's primary certification authority has been China's Civil Aviation Administration. While CAAC requirements are robust, reciprocal validation by ESA or FAA involves extensive review. Without these international certifications, airlines outside China face regulatory barriers to operate the aircrafts in their own jurisdictions. Obtaining global certification is neither quick nor guaranteed. It requires demonstrating compliance across every system and operating condition backed by extensive flight testing, engineering analysis, and safety data. Even Western manufacturers spend years refining designs to secure approvals. A critical question for airlines is how a new aircraft performs compared to existing options. Performance covers fuel efficiency, range, payload, maintenance intervals, reliability, and operating costs. Airlines make purchasing decisions based on how many seats an aircraft can carry with acceptable costs and how far it can fly without refueling. The C919's performance is competitive on certain metrics within its class, but it currently does not exceed the benchmark set by the latest A320neo and Boeing 737 MAX variants. Fuel efficiency gains in modern aircrafts come from engine technology, aerodynamic design, materials science, and software optimization, areas where Western manufacturers have invested heavily over decades. Because the C919 uses engine and systems technology that is proven and robust, but not the absolute latest available, its range and fuel economy are in line with industry standards, rather than clearly superior. For many airlines, that is acceptable. For others, especially those operating long narrow-body routes, the economics favor the most efficient airplanes available. Designing an aircraft is only part of the challenge. Producing it reliably and at scale is another. Boeing and Airbus have spent generations refining their supply chains with established Tier 1 and Tier 2 suppliers around the world. Those relationships yield predictable quality, delivery timeframes, and risk mitigation. COMAC is building its supplier network and manufacturing systems, but it still relies on external partners for major subsystems. Developing indigenous production capability takes time, investment, and expertise. The global aerospace supply chain is not only about making parts, it is about ensuring traceability, quality control, certification standards, and consistent delivery across thousands of components. Additionally, aerospace production rate is a measure of efficiency. Airbus and Boeing currently build dozens of narrow-body jets per month between them. COMAC's output remains modest by comparison. Higher production rates require not just factories and workers, but trained engineers, sophisticated tooling, and resilient logistics. Factors that take years to mature. Airlines do not buy an aircraft in isolation. They buy support, spare parts, training for pilots and mechanics, global maintenance networks, avionics updates, and continuous technical assistance. Operating an aircraft's type involves establishing a long-term ecosystem that touches virtually every aspect of an airline's business. Western aircrafts benefit from decades of global support infrastructure. Independent maintenance organizations, simulator providers, spare part distributors, and training academies exist worldwide for Airbus and Boeing family aircrafts. This network reduces operational risk and cost. For the C919 to gain traction outside China, COMAC and its partners would need to build a comparable global support footprint. That means facilities, distribution agreements, training centers, and regulatory approvals in multiple regions. A massive undertaking. To date, most of the C919's orders and deliveries have been to Chinese airlines and leasing companies. That reflects both national industrial policy and the size of China's domestic market. China has one of the largest and fastest growing commercial aviation markets in the world, with hundreds of airports and thousands of routes that can absorb new aircrafts. For Chinese carriers, operating a domestically produced aircraft has strategic appeal. It supports national industry goals and reduces reliance on foreign suppliers. However, for international carriers, the calculus includes evaluating total life cycle economics, operational compatibility with existing fleets, and regulatory acceptance. Airlines consider risk carefully. Adopting an aircraft with limited global support and uncertain long-term parts availability represents a business risk, even if operating economics are reasonable. The absence of a mature ecosystem weighs heavily on decisions. A broader theme in aerospace competition is the tension between replication and innovation. Established manufacturers invest billions in research and development, often absorbing the cost over decades of sales. These investments focus on lighter materials, more efficient engines, advanced aerodynamics, and digital systems that enhance safety and performance. COMAC's approach incorporates lessons from existing designs, which is practical and common in technology development. However, building a truly innovative platform that leapfrogs competitors requires sustained investment, ecosystem integration, and experience across multiple aircraft programs. Innovation also ties into regulatory trust. Authorities and airlines alike gain confidence through consistent performance and incremental improvements over time. That trust is as valuable as any technical advantage. The C919 story is far from over. It represents a significant step for Chinese aerospace and a demonstration of capability that would have been difficult to imagine a generation ago. Its existence adds diversity to the global aircraft's landscape and provides real choice for airlines, especially within China and potentially in emerging markets. However, competing at the global level involves more than building an aircraft that looks capable. It requires ecosystem maturity, performance that meets or exceeds global benchmarks, certification acceptance across major regions, a robust supply and support chain, and the confidence of international operators. The headlines that sensationalize ghost plane theft overshadow the more meaningful narrative, the challenge of breaking into an industry defined by high safety standards, complex engineering, and decades-long customer relationships. COMAC's journey illustrates how aerospace competition unfolds in real terms, where industrial ambition meets the realities of certification, manufacturing, and market economics. China's C919 is not a simple clone of a Western airliner. It is the product of a deliberate industrial strategy, international cooperation, and years of technical development. The fact that it has not yet become a global bestseller does not signal failure. It reflects the inherent challenges of scaling a new aircraft program to international standards. Even from a purely economic perspective, the C919 doesn't yet offer a clear competitive advantage. It's similar in price, performance, and efficiency to the Airbus A320neo and Boeing 737 MAX, both of which are already well integrated into global fleets. Without offering better fuel burn, lower emissions, or superior economics, the incentive to switch just isn't there. Then there's the geopolitical dimension. The C919 is entangled in US-China trade tensions. Some of its critical components, including its engines, rely on Western export licenses. Any future dispute could disrupt that supply chain, posing unacceptable risks for airlines in politically sensitive regions. That makes decision-makers wary. Finally, leasing companies, who finance a majority of airline fleets, remain hesitant to invest in the C919. These firms value liquidity. They want aircrafts that can be leased, sold, and released anywhere in the world. Without broad certification and resale appeal, the C919 is a hard sell in financial markets, further dampening its international prospects. Thanks for watching. If you found this deep dive into the world of global aviation insightful, make sure to like the video. It really helps us bring more stories like this to you. And if you want to stay ahead of the curve on everything from aerospace breakthroughs to untold aviation histories, don't forget to subscribe and hit that notification bell so you never miss an update. See you in the next one.